Okay, here's your lesson summary for topic C4, electrolysis half equations. This is lesson 15 in the book, and this is for those doing the higher papers. So, quick reminder of electrolysis. We've got our electrolyte. This is in a molten state in our container. We've got two electrodes. We've got our anode and our cathode with a direct current used to connect the two. In our electrolyte, we've got positive ions which come from our metal, and we've got our non-metal negative ions. When the positive ions arrive at the cathode, they're going to change from being ions into atoms. And in order to do that, they're going to have to gain an electron. So here's an electron here. It may be more than one, depending on the ion, but there's definitely going to be some gain of electrons. So this acronym oil rig, reduction is gain. So the metals here are going to gain electrons, so this is going to be reduction. So the point of this part of the process is so ions can turn into atoms, and we'd see solid metal either as maybe or even as a liquid. Possibly we might have a metal coat in the electrode. It depends on the metal that we're going to use. Over to the the anode. We've got our negative electrons. These are our non-metals. When these ones arrive, these are also going to be ions, but they're going to turn into atoms. These are going to do that by losing electrons. Oxidation is loss, so we've got oxidation happening here, and the electrons are going to flow around the circuit and to the other side, and this completes the process of electron transfer. So we've got reduction happening at the cathode, and we've got oxidation happening at the anode, and the whole process is designed to turn ions into atoms. Now, what happens next with these atoms, that varies depending on the substance that we're using, and that's where the half equations can be useful. So let's have a look at what happens with the example of lead bromide. So we've got lead, which is our metal, and bromide, which is our non-metal, and hopefully you can see that the colours match up. And this is the formula PbBr2, and the reason for that is because lead has is a positive ion with a charge of 2, so we've got Pb with a 2+ ion. And what will happen here, we know that it's going to gain some electrons, so in this case it needs to gain 2 electrons in order to cancel out that positive charge, and as a result we form Pb lead metal. The bromide, again, every bromide ion that's going to turn up is going to lose an electron, so we've got a bromide ion is going to lose an electron which has a negative charge. However, bromides, when they turn into atoms, they don't stay as single atoms. They actually form bromine molecules. So it's Br2, which means we've got to go back to the equation and just balance it up. So I need 2 bromides to lose 2 electrons in total in order to make a bromide molecule. And this is common through the with all of the halogens. Right then, let's move on to the next side. Next possibility was when we look at dissolved electrolytes. So this time, because we're using water, we might have hydrogen ions and hydroxide ions to deal with as well. So let's look at a couple of examples, because there's a couple of rules that we need to follow with this also. Let's start with our positive ions. So if you have hydrogen as the substance that's going to react, what will happen with hydrogen, we'll get a hydrogen ion. Our hydrogen ion is going to gain an electron, and that is going to form a hydrogen atom. Now hydrogens also pair up to form molecules. As a result, then we need 2 hydrogen ions to gain 2 electrons. Now sometimes we don't produce hydrogen and we might produce a metal. So for example, if you had copper in this case is going to be a Cu2+ charge. This one is going to gain 2 electrons, and as a result is going to form just copper atoms. Now we always choose the least reactive. So if your electrolyte contains hydrogen or copper, what you're going to find is that copper is less reactive than hydrogen in the reactivity series, so you're going to produce copper ions instead of hydrogen ions. If you look in the reactivity series, and if your metal, such as lithium for example, is more reactive than hydrogen, then this is the equation that you go for. So we always choose the least reactive when we're talking about a choice between different ions at the cathode. At the anode is a slightly different story. We're going to have a look and see what happens with the hydroxide ions, and then we're going to look at an alternative to that. So with the hydroxide ions, we'll have OH minus. This OH minus is going to lose an electron, and that then is going to help us to produce some oxygen, and we're going to get some water. Now we can't possibly get an O2 molecule and a H2O molecule from a single hydroxide, so we have to balance the equation up. Now we need 4 hydroxides to lose 4 electrons in total, and that will allow us to make an oxygen molecule and 2 water molecules. So let's just see if this balances up. 4 oxygens, I've got 2 here, and I've got 2 from my water molecules. I've then got my 4 hydrogens, and these are used to make the 2 H2s, and the extra electrons allow me to do that. There is an alternative way to write this that you may see in revision guides or books, and that is because the hydroxides, you could write these 4 electrons on the other side, but you put a plus sign. Now, if you have a halide present, now a halide is anything in group 7, so if you have a halide, then the halide behaves in, we get a similar reaction to what we had here. So this is bromide. Let's do fluoride, and just so you can see how this compares. So we have a fluoride, which is F minus. All the halides have a single negative charge. It's going to lose an electron, but they also form molecules with 2 atoms. And as a result, then we just need to go back and balance. Okay, so here's all your different examples of half equations for the electrolysis process in topic C4.